what's going on, guys. Miss Hellman bathroom.
What did you just say?
Small box.
She's like, now I gotta restart.
Kind of. Okay, you threw me off. So today we're going to talk about two theorems. They don't really give us, we're not going to use them to like solve big problems, but the concept is important for us to consider. Okay, we're going to talk about two theorems, Raleigh's theorem and the mean value theorem. So first we're going to talk about Raleigh's theorem. Okay? You and your pod, I want you to come up with 3 different graphs that go through A and B and are both continuous and differentiable. Okay, so I'm going to give you 1 minute. Make 3 different graphs that meet those specifications. Continuous, differentiable, go through A and B. It doesn't really matter where you put the points.
I would have thought more like
All right. Eli, show me one of your graphs.
I got a straight line between two.
Ooh, who else had a straight line? I should just say line because all lines are straight, right?
Straight
Okay.
horizontal.
Thank you. Okay. All right. Pod 1. Let me see one of your graphs. Okay. Say one out loud. A parabola. Opening up or down? Okay. Okay. Pod 6 back there. Describe me one of yours. That's different. So kind of like that? Okay. Each and every one of these graphs and the others that you drew on your paper, if they're not up here, have one thing in common. Besides passing through those points. Obviously they have these things in common, but they have one more thing. They all have at least one time. They all have at least one time where
They cross the y-axis. That crosses the y-axis.
oh, the y-axis. Well, okay. So yes. Sorry, I interpreted X. You said Y. Okay. That happens because we're in 2 different quadrants. Okay. There's at least one time or more in each of these graphs where the derivative is 0. Here there's 2 places. Here there's 1 place. Here there's... Okay. Why is that happening? Our 2 values, our 2 x values have the same y value. So no matter what we draw in between those 2 points, as long as it's continuous and differentiable, you will at one time or more have a moment where the derivative is 0. That is what Raleigh discovered. Okay, and when you're a mathematician and you discover something, you get to name something after yourself. So differentiable means, well, let's talk about non-differentiable. We cannot differentiate if there's any discontinuities. We cannot differentiate at corners. And we don't have a derivative that exists if it's an undefined slope. Does that make sense? Okay. So the big things we're worried at, if we already know it's continuous, we're really worried about the undefined slope and the corner piece. Okay, so Raleigh's theorem is just what we talked about on that last slide. As long as our y values are the same, then somewhere between those two x values, you're going to have a slope of 0. Do I need to move it up a little bit? Better? Okay. So when I give you a function, okay, you need to check 3 things first. Number 1, is it continuous on the closed interval? Okay. Number 2, is it differentiable on the open interval? So it doesn't, the endpoints don't matter, but in between, are we differentiable? And then number 3, are our y values the same? And if we meet those 3 stipulations, then we can find that one time or more that we have a derivative of 0. If you do not check for continuity and differentiability, I will take off points on your test. Do you understand? So, I'm going to put up a problem, and I'm going to show you exactly the work that I would expect to see on Thursday, Friday test. Okay? So what I would write down is f of x equals x squared minus 2x on the interval 1 to 3. And then leave out the rest of the words because it's right under Raleigh's theorem. You'll know that that's what we're doing. Okay, now I know you're going to look at this and think, oh, it's a parabola. I'm good, right? But just show me that you thought about the continuity from -1 to 3. Is this parabola continuous from 1 to 3? I see some head shaking. Yes, so give me a little check mark. I thought about it. Okay. Is this parabola differentiable on the open interval -1 to 3? Okay, it's a polynomial, right? We're fine. Okay. So now I need to figure out, okay, if I can use Raleigh's theorem or not. And the only way to use Raleigh's theorem is if -1 and 3 have the same function value. So when we plug -1 in for f, -1 squared minus 2 times -1 would give us 3. And 3 squared minus 2 times 3 would give us 3. So there we go. So we can apply Raleigh's theorem. And Raleigh's theorem says that somewhere between -1 and 3, there's at least one time where our derivative equals. So let's find it. Our derivative would be 2x minus 2. And I want to know where that equals 0. Colby, where does that equal 0? X equals 1. Okay. Now, most often they're going to ask for a C value. They're basically just asking you for the specific X value. We solved for X is 1, so C is 1. Okay. Now, if this were the example that Pod 6 had given us to draw up there, we would have had 2 answers, and we would have found both of them in our algebra. Okay, but in this particular example, we only had 1. Okay, that was a pretty straightforward problem. Let's stretch our brains a little bit. Turner, are you okay back there?
Yeah, I was just wondering why we had to find f negative 1 and f of 3 was 3. Why did both do that?
Our y values have to be the same in order for us to apply this theorem. The only way that we're guaranteed a slope of 0 is if our points have the same y value, because their slope is 0, essentially. Okay, how about this one? F of x equals x to the 2/3 minus 1 on the interval -8 to 8. Okay. Is this function continuous? From -8 to 8. We're not going to have like any asymptotes or anything like that, right? We don't have a rational. We're not having any holes. We're good. Okay. Is this function differentiable from -8 to 8? And says yes, wait. Yes. Please keep in mind, we don't want our derivative to ever be undefined. If our derivative is undefined, it's not differentiable there. What is our derivative? Two-thirds x to the -1/3. And what happens to that x to the -1/3? It goes to the denominator. And would there ever be a time between -8 and 8 that the denominator of our derivative would be 0? Yes. Which means it's not differentiable. Okay, so Raleigh's theorem cannot be applied. Which is why it is important for you to check those 3 stipulations. Okay, is it continuous? Is it differentiable? Are our y values the same? Okay, I am going to give you an example that I want you and your pod to work through. Oh my goodness. There we go. However, that needs to be a bracket. Yeah, I'm typed in backwards here. Okay, so apply Raleigh's theorem to f of x equals x to the 4th minus 2x squared. on the interval -2 to 2. Don't forget to talk to each other while you're doing this. Well, first, I was asked, are there just one or two? Rows in your interval, okay. Second way is like this.
That's the actual, that's exactly.
Oh, yeah.
On the end, exactly.
Half price.
Right, now if I give you the interval from, except for the one side. Okay, is this function continuous and differentiable?
Yes.
Okay, I know that it's an automatic if it's polynomial, but you better write this right here so I know that you checked it. Okay, if you don't, I'm not giving you full credit. Okay, yes.
Just a quick question. Why does it change from brackets to parentheses for differentiable?
Because it doesn't matter if it's differentiable at the end points or not. It's more about what's in between. Okay. Were your y values the same?
Yes.
What were they?
8 to 2.
Okay. And then you found your derivative, which was 4x cubed minus 4x. And so your c values were plus or minus 1 and 0. Yeah. Awesome. Okay. So now let's talk about that MVT that I have written up there, the mean value theorem. And this is probably the one that you are going to see most often, but there are a lot of similarities. It's actually, Raleigh's theorem is kind of a special mean value theorem. So the mean value theorem, once again, we are continuous on the closed interval, differentiable on the open interval, but this is now what is happening. And what I'm going to have you do is just write it down, and then once it's written down, we can process through it.
Bless you.
Okay, so in Raleigh's theorem, we had to make sure that we were the same y value, and we looked for when the derivative was 0. Okay. Now what's happening? What is this right here? It is slope. Okay. Back in Unit 2, we talked about the slope between 2 points being the average rate of change. Do you remember that? Okay. So the mean value theorem is essentially when is the instantaneous rate of change equal to the average rate of change? When is the derivative equal to the slope between the 2 points? Okay? Because it's going to happen every time. If you have 2 points and you draw a line between them, whatever that slope is, you're going to have at least one time on your curve where the tangent line has that same slope. Okay, so now that's what we're going to find. Okay, when is the average rate of change equal to the instantaneous rate of change? And just like in Raleigh's theorem, we're going to make sure it's continuous and differentiable. Okay, so let's talk about this example right here. So we are still needing to find the y values, but we're going to actually use the y values to find our slope. Okay? And just like in Raleigh's theorem, we have to check for continuity on the closed interval and differentiability on the open interval. X to the 2/3, is it continuous from 0 to 1? There aren't any asymptotes or holes because it's not rational, okay? And it's not a piecewise function, so we don't have to worry about that. So it's continuous. The differentiability, I'm curious about. Makes me nervous because of that fractional power. What is the derivative? Where would it not be differentiable at? 0. So are we differentiable on the open interval 0 to 1? Yes, we are. Because 0 is not included. It's the end point. It doesn't have to be differentiable on the end point. Just in between the end points. Okay? So we actually can apply the mean value theorem to this function. Okay? So this is what we are going to do. We need to calculate the average rate of change. So what's the slope between 0 and 1? Okay, so we're going to plug in our function values in. F of 0 would be 0, F of 1, 1, that's kind of boring, right? Okay, but our slope, our average rate of change, y minus y over x minus x would be 1. Okay. And what we want to have happen is we want our average rate of change to equal our instantaneous rate of change. So we want our derivative 2/3 x to the negative 1/3 to equal 1. I'll even put a little note here. Our derivative, we're going to set equal to the slope that we calculate. Okay? Now it's just a matter of algebra. Any thoughts on what you want to do to solve this? Okay. So x to the negative 1/3 would equal 3/2. Okay. Now, to get rid of the negative 1/3 power, okay, but since it's negative, it'd be a negative cube. Which all that means is 3/2 cubed would be 27/8. So 3/2 to the negative third would be 8/27. Because we'd have to flip it. Okay. So our C value is 8/27. You all have your calculators, so, but please keep your numbers nice for me, like 8/27. Don't give me a decimal. If it's a nice number, keep it as a nice number. Okay. Questions on what we did here? Okay. Raleigh's is a special mean value theorem. How so? Okay, and Turner, what is the slope between 2 points who have the same y value? 0, okay? So in Raleigh's theorem, your two coordinates had the same y value. We were setting our derivative equal to 0, okay? We're still doing the same thing. We're setting our derivative equal to the slope between the 2 points. We're just not actually having to find that slope, okay? So the mean value theorem, Raleigh's theorem is just a special case of it when your 2 points have the same coordinates, or the same y coordinates, sorry. Okay? All right, we have 3 extra minutes. Do you want to do one more example?
I feel pretty good, but we got this.
How about like just a polynomial example? What?
I have to go pee.
We have like 3 minutes. Like you can't.
I can not.
Okay, so this is polynomial. That makes it easy, right? Are we continuous and differentiable? Then what do we do? Okay. So with those 2 points that we calculate, we're going to calculate the slope, which is
3/1.
okay. And what are we going to do with that slope? We're going to set it equal to the derivative. And the derivative of x squared plus 2x minus 1 would be
2x plus 2.
So it's equals what?
5 halves. No, 1/2. 1/2. 1/2. Hey.
Look at that. We did a problem in 2 minutes.
Yeah. Now,
Well, we'll have to see. Okay? I would say the biggest challenge you're going to have is determining if it's differentiable or not. That's when you're going to have to think a little bit. Okay? Otherwise, it's very straightforward. I'm not trying to fool you at all.